Hi everyone, and today we are going to consider some integrals that will involve the residue theorem. And for this kind of integrals, the function will only be containing either sines or cosines. So you can see that I have already written out an integral that looks like this, and the limit for the integral is from 0 to 2 pi, and the function will have only sines or cosines in it. And we will see how we can use the residue theorem to evaluate such integrals. So if you want an example that what kind of integrals I'm talking about, it can be something like this. So the example that I'm going to show you is, let's say you're considering an integral that looks like this: 0 to 2 pi d theta by 1 plus a sine theta, something like this. Or it can even be something like this: 0 to 2 pi e to the power I theta divided by sine theta minus b. Stuffs like this. That means the function itself will only involve the sines and cosines. So let us try to see the theory behind evaluating these integrals. And obviously we are going to promote the real variables into the complex variables, but see here that we are having our angle as a integration variable, and we are also saying that the integration limit is from 0 to 2 pi. So this gives us an idea that the contour we are going to choose will be a circle, because a circle can be parameterized with a radius and the angle itself. And since the limit is from 0 to 2 pi, and also it's just involving only sines and cosines. See, in this argument I have only sine and only cosine, and you can think of this sine as 1 times sine theta and 1 times cosine theta. So that tells you that we can choose a unit circle to parameterize the contour that will help us in evaluating integrals of this kind. So let me draw the contour first. This is 1, let's say this is -1, and this is our contour. So this is a unit circle. That means the radius is 1, and this circle is parameterized by z is equals to e to the power I theta, right? Since the radius is 1. And now the first thing we are going to do to evaluate this integral, let's say we are going for this integral over here. So we want to evaluate this one, and if you recall that sine theta was written as e to the power I theta minus e to the power negative I theta divided by 2i, and cosine theta was parameterized or written in the exponential form as something like this, right? And all of these are complex variables because it's a e to the power I theta or something. And if you see over here that we are saying the circle itself is parameterized by e to the power I theta, that is denoted with z. So we can write sine theta as z minus z inverse 1 divided by 2i, and there is a z plus z inverse 1 by 2. Why z inverse 1? Because 1 upon e to the power I theta is equals to 1 upon z, right? And that's just z inverse 1. So that's the reason I am writing it as z inverse 1. So now we have already promoted our variables, that is the integration variable theta, into the z thing. That's the first thing to do. That is, we are promoting our real variable into the complex variable. And now, since our original integration contained this d theta term, as you can see over here, oops, there should be a d theta, and we have to substitute this d theta in terms of dz. So our parameterization tells us that z is equals to e to the power I theta, right? So dz by d theta will just be I e to the power I theta, right? But e to the power I theta itself is z, so this is just iz. And from here you can write that d theta is equals to dz by iz. Okay, so finally we are done. That is, we have set up the recipe to how to integrate this thing, and you just have to now put it over this thing over here. That means instead of sine theta you write z minus z inverse 1 divided by 2i. Instead of cos theta you write z plus z inverse 1 by 2, and instead of d theta you write this thing. So this 0 to 2 pi f of sine theta cosine theta d theta, this becomes a contour integral over the unit circle in the complex plane, and now the arguments change as follows. And using this we are going to evaluate this integral over here, and let us see how we can do it. And obviously, since I mentioned a contour, I have to choose the orientation, right? And the default orientation is just the anti-clockwise direction. That's the default orientation unless stated otherwise. So let's try to do this example with the help of the theory that we just developed. So this is our example 1, perhaps the only example we'll see in this video. So it was d theta divided by 1 plus a sine theta, right? So this is our original integral, and here there is a condition on a, and why this condition is important is something I'm going to explain you a bit later. That a lies between -1 and 1. It's greater than -1 and less than 1. So if you follow this theory that we just recently developed, then first you need to use dz by zi instead of d theta, and instead of sine theta you have to write this thing, z minus z inverse 1 divided by 2i. So let's try to do that. So we are now promoting our integration to the contour integration, and we are going to write dz by zi. This is coming instead of the d theta, and let's write this thing in bracket. So you have a, you had sine, so instead of sine you will have z minus z inverse 1 by 2i. And now what you need to do is that you need to simplify this a little bit as far as you can, and you will see that there will be a polynomial that will appear in the denominator. So let me do that. Oops, there should be a minus. Now I have a z inverse 1 over here, so I'm going to write it as 1 upon z, and then I'm just going to do the algebra so that this whole thing only contains positive powers of z. So at this point I'm just doing nothing but just simplifying this whole mess. That's it. There is nothing new around here, and yes, there should be a. So this becomes 2iz, and there will be az squared minus a, and there should be a 1, there will be a z in the denominator over here, that means over here, and if you write it directly it will go upstairs. So let me just write that directly. and there was a 2i. Now you can see that this I cancels out. You have a 2. So write the contour integral as, and yes, this z and this z also cancels out. So finally what you have is z, 2 dz times az squared plus 2iz, and finally minus a, right? And our contour was this unit circle. It doesn't look like a circle, but let me just draw it again so that, okay, it still doesn't look like a circle, but it's a circle, all right. So now we are going to use the residue theorem that you already know. So we're going to write it as 2 dz az squared plus 2iz minus a, and this is equals to 2 pi I, the sum of the residues, that this contour or this unit circle contains inside it. So to find the residues, the first thing you need to do is that you need to find the poles. So now we'll find the poles, and that can be done via az square 2iz minus a, and you demand this to be 0. This is a quadratic equation and you know how to solve it. So let me just write down the solution. The reason I'm putting a plus here, because it should be b square minus 4ac, where 4 comes first and a means this first coefficient, because I'm comparing with this equation over here, ax squared plus bx plus c, the standard quadratic equation, and the c term comes with a minus sign, so minus minus, there is a plus. Okay, so ultimately this is just, oh yeah, there should be divided by 2, 2a, where a is this small a over here. So now you just simplify this whole thing. Now you can see that this is a pretty convenient format, but yet it's not quite. What I'm going to do right now is that since a is between minus 1 and 1, you can see over here that the first thing we wrote down when we were trying to solve this integral, it says that since it's less than, since it's staying between minus 1 and 1, this a square minus 1 is actually an imaginary term, right? Because this a square minus 1 is a negative term and there is a square root over it, so it's a purely imaginary number. So for convenience, so I write it as 1 minus a squared, but when I switch this, switch from this a square minus 1 to 1 minus a squared, that means I'm taking a minus sign in common, or let's say I'm factoring out a minus 1, and I will also have a square root over it, so that should give me an I that will come outside this square root thing, and there's a divided by a, and finally you can write it simply as like this. So there are two poles, one comes with a plus sign, one comes with a minus sign, and let's call the plus z plus as I minus 1 plus 1 minus square root of 1 minus a square by a, and z minus as I minus 1 minus square root over 1 minus a square by a, like this. So ultimately we'll have these two poles, but now we need to know which pole lies inside the circle and which pole lies outside the circle. So again, let's try to draw the unit circle. So this is a unit circle, 1 minus 1 I. I'm just stating out the coordinates so that you can visualize it easily. Now if you notice, this z plus and the z minus, when they are multiplied, that means when you multiply their modulus, this is just what? This is just 1. If you multiply that, you'll see that the modulus is 1. Okay. Now that means either both of them are 1, or one of them is greater than 1, one of them is less than 1. So if you just calculate their modulus, you will see that no, none of them are equals to 1. So one of them is greater, one of them is less, greater than 1, one of them is less than 1, and they're in such a manner that they're when they're multiplied together, they give us just 1. Now the reason I'm showing you this, because it will help us to determine which one lies inside the circle and which one lies outside the circle. So if you notice z plus over here, you will see that since a is less than, a had this limitation, it was lying between minus 1 and 1. That means this 1 minus a squared is a positive quantity, right? It's a positive quantity. And you have this minus 1 plus some positive quantity over here. And at the same time, I don't care about the denominator so far, but I will, because it will be useful a bit later. And in the z minus thing, you will have a minus 1 minus a positive quantity. Okay. So this makes it a bit hard to understand from this z plus and z minus. So that's why we need to go to the modulus thing. So if you consider the modulus of z2, you will see that the modulus is just 1 plus 1 minus a squared divided by modulus of a, right? And this will be greater than 1. The modulus is greater than 1. So what does that mean? The modulus is a distance. So z2 lies outside the circle. This is somewhere z2 will be. I don't know the exact position, but it will lie outside the circle. But since the multiplication of their modulus is 1, that means that, sorry, I wrote z2. I should have written this z minus thing. Unfortunately, I wrote z2 and I have no idea why. It should be z minus. Okay, so sorry for that. So this z minus thing is lying outside the circle, and the way to determine is to just see the modulus of it and the condition that was imposed on a. And now since their z plus modulus times z minus modulus is 1, you will see that the modulus of z plus is less than 1. So that means this z plus lies inside the circle. So we will only need the z plus thing. We don't need the z minus to evaluate the integral. So now what we're going to do is that we're just going to use the residue theorem, and we can write this in a more organized manner. This 2z divided by this whole polynomial stuff. So let me write that down. Let's say this is z minus z plus and z minus thing, yeah, and this is just 2 pi I sum over the residues. But since there is only one pole, this will be just the residue. So let me get rid of this summation sign. and this residue is located at the point z plus. Now you want to calculate the residue for z plus, and this is simply 2 by z plus minus z minus. And if you do the z plus minus z minus thing, if you just look at these two guys over here, if I do a minus thing, this minus 1 and there will be a plus 1, they will cancel each other out, and I will have something like this. So this is just simple algebra, so I'm not decoding it for you over here. This is just 1 minus a squared by a, something like this. And if you just do it, it's just this thing. This is our residue, right? Oh yes, there should be an I, because I factored out an I in the overall z plus and z minus, so that's why there should be an I over here. And let's keep the I in the denominator, that makes things convenient. And finally you put the residue inside over here, that is this thing. So our contour integration was 2 dz by z minus, I'm just writing it in the factor mode because I don't want to go through the whole polynomial thing. And this is just 2 pi I, and the residue was a divided by square root over 1 minus a squared, and there was an I in the denominator. This I cancels out, and you will have a result something like this: 2 pi a 1 minus a squared, and there's a square root over it. But this integral was equals to what? This integral was equals to 0 to 2 pi d theta 1 plus a sine theta, right? So finally you will have the result that you desire. That means we wanted to calculate this guy, then we went to the contour integration methods. The residue, we applied the residue theorem, we made some arguments by using the restriction on a to determine which pole was inside the circle and which pole was outside the circle, and finally we end up with the result that looks like this. So this works when your limit is from 0 to 2 pi and the functions, that is the integrand, is only a function of sines and cosines. And this will be it for today, and I'll see you guys on the next lecture. Thank you.